so oh, first of all, I'll pass these around. These are blanks of this version. Do you have one already?
Yeah, from last week.
Can I get one?
I've been working on it.
Okay, so I want to do something a little different today. The solutions are already posted, so I'm not going to solve the problems for you. That's not the point of this exercise. Okay, yeah, enter Michelle, Farah, Andrew, Pico, Jonathan,
I'm pretty sure I get worse than
Christine,
I didn't say school first.
I did worse than you,
This is the
man.
worst I've ever done in all of college.
Me too,
On
man.
anything, like
Lilian,
in a row. Too long.
Bro, look, I did worse than you.
Yo, Alex,
What'd you get?
other stuff? Okay,
I'll show you, man.
Shit, you beat me. You beat me.
oh,
Guys, remember the final. The final roll.
fine.
So we did it.
You guys are focused on things too much. I mean, I decided to curve this test because some of you I realize will feel the sting of the grade, and I want to lessen that a little
Oh,
bit.
so this is our curve
But-
grade?
No, that's not the curve. So, yeah, that would have been, yeah, let's curve it and you still got, like, yeah, no.
What do you get?
But
What do you get?
again, the grade isn't important, like, the final is important. That's how I want you guys to think.
What matters is that I know the material.
Now, and again, the solutions to this are online, so I don't want to rewrite the solutions. I kind of want to go through and talk about kind of the things that we were talking about earlier, not necessarily the actual solutions, but the approach. What would I think about? What would you notice? How would you choose a strategy? That sort of thing. All the things that come before, that precedes you writing down a solution. So when you see a limit, any limit, what do you think? What goes through your mind when you look at this on the paper? The first things that are going through your mind. Tell me.
Well, this question.
Factor?
Yeah, factor.
Well, no, that should not be the first thing that goes through your mind.
Oh, to plug it in.
Plug in should be the
Yeah.
first thing that goes through your mind. Okay, here's a limit. I'm going to try to plug in the number. Okay, that should be the first thing. Okay, now, you'll notice that if you plug in the number, this would give you 4. That would give you plus 2. That would make a 6. Minus 6, you get 0. So, unfortunately, plug-in does not work. But it's important that that's the first thing you think about. Okay? What would be the second thing? Okay, plug-in doesn't work. What's the second thing you think about? Now you try to want to simplify it to see if I can plug in. Simplify, right? Which in this case is going to be factor. Okay, so now you have that thought. Okay, factoring is what I want to do. How would you go about doing that? Now when you understand that factor is what I'm looking at, now what is the first thing you think about?
You find to see what. Wait, first thing to think about?
First thing you think about. Once you decided plugging in is not going to work, hey, I'm going to try factoring.
Find-
Once you made that decision, I'm going to try factoring. What's the next thing you think about?
Find the number that is close to like the x's approach. I don't know.
No.
We try to get it in like x something times x.
That's the first thing you think about when factor. When you say I want to factor something, that's the first thought that comes to your mind.
Get into like binomials, multiply by each other.
Common terms should be the first thing you think about. I want to factor. The very next thought after saying I want to factor is what are the common terms. So once you choose factor, you are going to think common terms. So now you realize, okay, I see a limit, my first thought, let me try to plug it in. Okay, doesn't work, now what? I should try to simplify, I should factor. Once I try to factor, common terms is always going to be the first thing I'm looking for. And you will notice in the top, x squared is a common term.
Oh, I don't want to see
So now you're like, oh, in the top, x squared is common. Right, so what you're going to do is you're going to factor that out. You're going to have x squared plus 5x plus 6 left over. While at the bottom, there is no common term, so the bottom just stays as x squared minus x minus 6. Now do you see what else to do?
I would do.
Now these are just quadratics. So now you think, well, how do I factor quadratics? And that's when you try the foil, the reversing the foil. That's when you start thinking this and that. And you realize these guys would actually factor and give you something. So in
The
this,
thing is, I got negative 5 plus 6 that one time. I don't know if I got this version.
and this would be x. This would be, say, a minus 3 and a plus 2. Okay, so that would cancel. And now, if you plug in minus 2, the denominator is not 0. At this point, just plug in minus 2 for all the x's. That's your answer.
Wait, what?
Plug in minus 2 for every x.
Oh, okay.
Remember, the strategy for a limit is to try to plug in. If that doesn't work, you simplify so that you can plug in. So the thing I want to drill home here is, for every kind of problem, at some point I would have given you a list of strategies. Here's what you want to look for first, second, third. You cannot forget those strategies. They're important, because that's the difference between you. So the thing is, a lot of students will get into the issue of, they look at this and they're like, oh my god, there's an x to the fourth. What the hell am I going to do with an x to the fourth? The moment you think that, you're on the wrong road. It doesn't matter that there's an x to the fourth. It just doesn't. You see limit of something. Very first thought, I'm going to plug in the number. I don't care that there's an x to the fourth, or whatever it is, I'm going to plug it in and raise it to the fourth. It doesn't matter what it is. Right? It doesn't matter if there was an x to the fifth, an x raised to the radical 2 power, it does not matter. I'm going to try to plug in the number. Right? Now if I can't plug in the number, okay, it divides by 0, or there's a negative under a radical, or something crazy is going on, then I try to think of something more complicated. Then I'm going to be like, simplify. Now simplify can come in various ways. Right? It could mean, multiply top and bottom by the LCD, multiply by the conjugate, or whatever. But usually here, if you have a ratio of polynomials, simplifying means factor. If you have a division, not even just ratio of polynomials, division kind of in general, you reduce a division by canceling terms, common terms in the top and bottom, which requires factoring. The moment you decide factoring, the very first thought should be common terms. That is always the very first thought. You don't worry about, well, it's not really a quadratic and this and that. That comes after. Like I said, you really want to start global. Look at the big picture, right? In general, if someone were to say, how do you factor how do you simplify a fraction? Without them telling you any specifics, you should, the first thing I try to do is factor the top and bottom and then cancel the common terms. You should know that ahead of time. It doesn't matter what the fraction looks like. That's the strategy. Factor top and bottom, cancel common terms. That's how you simplify any fraction. And then someone might ask, okay, how would you factor the top and bottom and cancel the common terms? Well, if I'm going to factor, the first thing I would do is look for the common terms. Right? That's the GCF. That was step 1. When we went over factoring, I told you, here's the steps. You need to know those steps. You need to know, okay, first thing I'm going to look for is common terms, factor them out. Second thing, if there are 2 terms, I'm going to look if it's a difference of squares, difference of cubes, or sum of cubes. If it's 3 terms, I'm going to see if it's a quadratic that I can do the FOIL for. If it's 4 terms, I'm going to do factor by grouping. Right? You need to know the general approach in your head. So when you look at a problem, the specific problem is kind of irrelevant. You would do the same thing no matter how the problem looks. Right? So So that's kind of where you want to be. You want to have a command of the material that doesn't really care about the specific example you're looking at. You want to talk about, oh, it's a limit, plug in. If I can't plug in, simplify so I can plug in. If I can't do that, oh, maybe it's one of those things where it's top heavy or bottom heavy. And for that, you have to realize that, oh, this needs to be infinity, so that's not the strategy, right? The specific things don't matter, right? So if there's an x to the fourth here, don't go, oh no, there's an x to the fourth. What do I do with that? It doesn't matter that it's an x to the fourth. Right? The strategy is not going to change. So a lot of times what happens is students see something and they freak out. And what happens is, and again, this is kind of, they do things that they wouldn't normally do, but that goes back to what I was saying earlier, is that once you enter freak out mode, your brain goes into this almost survival mode. It just starts doing things to get you out of danger, right? So once you realize, oh, once you get scared by a radical, your brain is just gonna, oh, just square it and get rid of the radical. Even if you're not supposed to square, the thought is gonna come to your head, just square it. That's your brain telling you, oh, I'm in danger, do whatever I can to get rid of the danger. I know a square gets rid of a radical, so let me square everything. Right? That's your brain just trying to escape danger. You need to understand that's what's happening to you.
That's what I.
So you need to understand there are some things that just aren't acceptable. And you also need to understand I should never be afraid. And how do you not be afraid? It's not worry about the specific example. Just look at everything as like it's just a blank slate where I'm applying some dead strategy who doesn't care about the specifics. I don't care there's an x to the fourth, it's a limit. I'm going to try to plug in, otherwise I'm going to factor, otherwise I'm going to do this. Right? When you go in with a plan, you're not scared anymore. Right? You know exactly what I'm going to do. I know if this happens, I'm going to do this, and if this happens, I'm going to do that. You're not going to feel afraid. Like you get afraid when you like don't have a plan. When you encounter someone like, oh my God, I don't know what to do right now. You're like a deer in headlights, and you just do whatever you can to get out of danger. You don't want to be that way. You want to have like strategies in your head. You want to understand the specific problems don't matter. The strategy matters more, right? So what I wanted to do for the recitation is not to actually tell you about the solutions because you can go read them. I posted this online. I want to tell you, what was I thinking when I did those solutions? Because that's what you need to be doing, right? Because if you start thinking down the wrong road, that's when a problem becomes harder than it has to be, and that's when you make mistakes, right? So yeah, so for the first problem, that's kind of where my line of thinking would be. And in general, so once I see this symbol, it triggers a line of reasoning in my head, right? I see this, you know what? I don't even care about that in the beginning. Once I see LIN, I immediately think, okay, I'm going to either plug in or factor or blah, blah, blah. You have a plan before you even read over there, right? Because over there matters less than what your plan is, right? So you have this plan. So you know, whatever comes afterwards, I'm going to try to plug in. That's how I'm going to go after it, right? If that doesn't work, you should know what your backup plan is. And if that doesn't work, what is the backup plan now? Okay? So that's kind of how you want to think. Now again, for the specific solutions, you can find that online. I really care that you guys are thinking about the problem the right way, that you have the right thought process. Now if you went to the second one, it's kind of hard to get this to line up with the board. Okay, so now you go to the second one. You see that? Tell me what you're thinking. A lot of you are gonna, oh crap, there's an x cube over next.
I simplify and apply common terms for the top and like the bottom, you know.
Yeah, well, almost. First, you should notice the phrases that are being used.
Yeah.
Right? You always want to know your goal. What am I after? What am I chasing? What's the
I'm
target?
trying to find
Right? So, okay, I should be finding vertical asymptotes. I should be finding horizontal asymptotes. And I should be finding holes. Now, you should immediately know what each of these mean, right? Not for the specific problem. I'm not even worrying about that, right? The first thing I'm noticing are these terms. Then I would immediately think about what each of these mean, right? So I should know this guy, the horizontal
It's
asymptotes,
y
well, that's just the infinite limits. That's the limit as x approaches infinity of the function. And that's the limit as x approaches negative infinity of the function. So I automatically know what this phrase means. This phrase means I'm going to do this. What does vertical asymptotes mean? This means denominator equals 0 and nothing cancels it. This terms mean it makes the denominator equal 0, but something cancels it. Right? Now I look at the problem. I did not notice what that looked like yet. This is the first time I'm looking at that problem. Immediately when someone tells me, find the vertical asymptote, the horizontal asymptote, and the hole's off, at first I don't care about what they're going to say. I care about, okay, vertical asymptote, what does that mean? Horizontal asymptote, what does that mean? Holes, what does that mean? And you want to say it in very simple language. I mean, limit is not very simple, but it's simple enough for you to get it. Basically what this should trigger in you, if you know you see a ratio of polynomials, that should trigger the top heavy, bottom heavy scenario, right? Now you know to set something equal to 0, that involves factoring the thing. So once you think this, you immediately start thinking of factor. And over here, you would immediately start thinking of factor. Once you think factor, you think
Finding common terms.
finding common terms. First thought after you realize factor. Okay? So you read the question. There are going to be some very esoteric language that has to do with mathematics, like what the hell is a vertical asymptote, right? People who are not in this class probably wouldn't know what those mean, so those are words that you really need to know what they mean. So I read this problem. This is what my mind thinks of first before I even worry about that example, right? So I know this is the situation that creates a vertical asymptote. This is the situation that creates a hole. This is the situation that creates a horizontal asymptote. In order to set something equal to 0 and solve that equation, I need to factor and set each factor equal to 0. So I know factor is what I should be doing. And once I think factor, I'm going to think common terms. That's going to be my first step. So if I look at the top, the common term is x. I'm going to factor out an x. Right? So this, I want you to really realize that this is the last thing I'm doing. I don't just jump in and start playing around with the functions. I take my time to understand what is being asked of me first. And then I take time to think about what strategy would allow me to accomplish that. Then I start thinking about, okay, what does it take to employ that strategy? So I figure out that I need to factor, so I probably do that. And then I do common terms. In the bottom, the common term is an x squared. And I would continue with the factoring. So this now, each of these are quadratics. So I apply step 3. So now in the top, it will have to, of course, be a 2 and a 1, positive 2, negative 1. In the bottom, it has to be a 3 and a 1, and I could put a positive 3 and a negative 1.
So the whole
Okay,
would be
so
1.
now I can immediately see what would make the denominator 0. So denominator equals 0 means my x is 0, or my x is minus 3, or my x is 1, right? Now I look, okay, does any of them get canceled?
Yes.
The 1 gets completely canceled.
That would be the whole.
Oh, boom, that guy is a hole. Okay, the x plus 3 does not get canceled. So this guy goes over here, vertical asymptote. What about the x? Well, I cancel only one of the factors. So the problem is still there. I still end up with a division by 0. It doesn't get completely canceled.
So what the
So the 0 also goes over here. Right? What creates a hole is something that would have caused a division by 0, but you end up canceling it out, so it's not an issue anymore. But technically it is an issue, it's just a different kind of issue. It creates a hole as opposed to an asymptote. Any factor that doesn't get completely canceled is a vertical asymptote.
So
And then,
Horizontal asymptote.
let's do this first. Okay, now when I look here, this is an infinite limit of a ratio of polynomials. I have a strategy for that. It's one of three situations. Highest power is on the top, it's going to be plus or minus infinity. Highest power on the bottom is going to be 0. Highest power on the top and bottom is the same as the ratio of coefficients. What do we have here?
0.
Y equals 0. It's bottom heavy. So my answer is this is going to be my horizontal asymptote. These two are my vertical asymptotes. And this x equals 1 is going to be the whole. Okay. So now this is the specifics. This is what the students would really read. But the thing is, you need to know what came before that. Because otherwise now I can just really change this problem. I could like throw in, by the way, this would have looked pretty much, the strategy here would not change at all if I did like, put a 7th power here and put like a 6th power here and put like a 4th power here and put like a 8th power here and put like a 7th power here and put like a 6th power here. Now some students will read that and be like, oh crap, an x to the 7th? Man, Javon is crazy. You know what? Nothing changes. The answer will actually be exactly the same. Right? So the point is, don't get bogged down by the specific example. It does not matter. What you need to worry about is the strategy. What each word means, how would you go about finding that? That's all that matters. Right? The only way this thing will change is that now over here instead of an x, I'll have an x to the 5th. And over here instead of an x squared, I'll have an x to the 6th. And those guys would actually cancel. I'll still have x's in the denominator, and it's going to be exactly the same answer. Right? It's not going to change. It will be exactly the same answer. And you could see something that looks even scarier, right? So I could do something like, okay, this is x to the 3 over 2, and that's x to the 1, and this is x to the half, and this is x squared, and this is x to the 3 over 2, and this here is x to the 1. You know what? It's exactly the same answer. Well, almost. I got ahead of myself here. Because the half is the square root, so the negative number wouldn't really apply. But you get, the strategy would be the same, but eventually when you get here, oh, negative 3 isn't even an issue. But yeah, the specific example is irrelevant. You need to know the strategy. When you're asked for something, you need to know if someone asks for a limit. Without them telling you what the limit is, you need to know how you're going to attack it. Because you see, when you go in, it's a different posture, you know? It's like, you see if you go into the test and you kind of think, oh my God, man, Javon always does hard tests, man. Like, he's going to try to mess me up with something. And that's the mindset you go in with. Any little thing that makes you uncomfortable, your brain is going to freak out. The moment your brain freaks out, you have to understand you're working with a lower level of faculties and you don't want to be in that situation at math exam. But when you walk into that exam and you kind of know, yo, if Javon does this, I know how to do that. If Javon does this, I'll do that. If Javon does this, you walk in with a prepared mindset. What happens is now, when you see something that's kind of jarring a little bit, you're not going to completely freak out. You're going to be like, okay, I see what you're trying to do, but it actually doesn't matter. I'm still going to factor anyway. Right? So that's kind of the mindset you want to have and how you want to actually look at these things. So understanding the terms is very important. So you need to know the definition of terms. You also need to be able to say it in very simple language, because yeah, tests are going to be a situation in which you're even a little bit anxious. Even most people, even who are good at math, might even feel a little bit of anxiety. So you really want to be able that it doesn't take a high-minded, sophisticated brain to get through this exam. You want to study things so that even if your survival brain who just understands very simple language take over, it'll still work out in your favor, right? Because you know how to express ideas in very simple terms. So I don't want you to worry about, oh, the examples might be complicated. you're already on a losing battle in that situation. You want to think, it doesn't matter what the example looks like. If I'm asked about this, this is what I'm going to do. If I'm asked about that, that is what I'm going to do. Oh, here was the one of them. Oh yeah, problem 4, a lot of people have trouble with that too, but let's actually talk about that. Didn't see problem 3. Okay, so we actually did this one in class. So I'm reading this. Okay, suppose f of x is blah. That's literally what I would say in my head if I'm reading this, because the blah doesn't really matter. Okay, suppose f of x is blah, find the equation of the tangent line. Boom. Right? Because when I start reading and I see the word find, okay, that's my target. I'm kind of hunting something. Okay, find. Okay, that's the important thing. That's the first thing in the problem I'm going to notice. Okay, f of x is whatever. Find. Okay, what do I need to find? The equation of the tangent line. Okay, what is the equation of the tangent line? Right, this is just y minus y1 equals mx minus x1, where the m comes from the derivative. At the point. Oh, what's the point? Oh, the point where x equals 1. All right, so this is where, so I know my x value is going to be 1. So I know my slope is going to come from the derivative evaluated at 1. Now I look at the function. Before, I didn't care. Right? All this went through my head before I even noticed the specific example. Because the example kind of doesn't matter. This strategy is going to work no matter what the example is. Now, when you want to employ that strategy, the strategy requires that you find the derivative of something. Now, okay, what do I need to find the derivative? Okay, that guy. But that's just a bunch of power rules, right? So I'm going to find the derivative now. That's going to be 2 minus 2x. Oh, that's another thing. Some people, when I ask them to find the derivative, they use the definition, the limit definition.
I thought
Like,
that's what you
only use that if you're asked for it. You never want to be doing the limit definition. Like, a lot of people are doing that. You were wasting so much time.
Because I thought you wanted us to do it for every question.
No, if I want you to do limit definition, I will specifically ask for it. There was a problem that says use the limit definition. That's the only time you should have done. Right? And now I'm going to plug in the 1. So the m would be, if I plug in 1, you would get actually 0. So essentially what happens is that this part doesn't even matter because the m is going to be 0. And so now I just need to know the y coordinate when x is 1. So I know my y1 is going to be 4 plus 2 times 1 minus 1 squared. And so that's going to be, what, 5?
Yeah.
So now I plug that in. Y equals 5 is the answer.
Wow.
The 0 was 3. Because I did it first and it got 0, and then I like, no, it can't be 0, and I went back and did something else.
Yeah, no, I'm not. Right, it's just, if it seems strange to you, just double check your work, but no, it doesn't matter. The 0 I would plug in here, and that's just going to wipe out this entire sign. Well, I never really did when does the recitation actually end?
2:30.
Okay. You have to leave?
Yeah, so
Okay.
I
All
want
right.
to stay, but...
All right, go. Okay, now this part here, now a lot of people messed up with this as well, and it's because okay, so now let's think about this. If I ask you where something is continuous, what is your first thought?
Factor.
Okay, no.
No.
A lot of people thought that, but that should not be your first thought.
So I
For us, you can almost, well, I shouldn't say that. Because it will be, for a piecewise function, that would be true. But for something like this, where it's continuous kind of means it's asking you for the domain. Because we have that theorem that if you're looking at there are 6 continuous functions, I mentioned this a while back, polynomials, rational functions, trig functions, exponentials, logarithms, radical functions. This is a rational function, And we know that all these functions are continuous on their domain. So if someone gives you a rational function, asks you where it's continuous, you just need to find its domain. That's it.
So just
Now, where would you find it? How would you find its domain?
you would do x, you would factor, and do x plus 1, x minus 1 on the bottom.
Right, you can factor, but it's very important that you realize you're not simplifying.
And then you do the timeline.
So here you know x cannot be 1 and x cannot be minus 1. That's it.
So if you just put that, is that wrong? If you just put x cannot be 1 and x cannot be -1 without doing the domain?
Well, here, yeah, because I never said use interval notation.
Okay, because I put that answer. I got
You put
it.
all x except x equals 1 or minus 1?
Yeah, that's what I put. I put
didn't.
x.
You show me afterwards. Then you can write this.
What do you say?
Although
Name.
interval method is preferred because usually on the final they're going to write it out in interval notation. Another way, yeah, you can say something like all x such that x is not equal to plus or minus 1. You'd have to type out that entire sentence. Okay, but the thing is, a lot of people here, what they did was they started simplifying and canceling stuff. And some people went as far as to say, okay, this would cancel, and so x equals 1 is the only bad point. And then they went and said, oh, okay, I just only have to avoid the 1. But that's not true that you only have to avoid the 1. The x plus 1 in this case would create a hole. It's still not going to be continuous there. You still have a division by 0 in the original function. So,
Wait, so is it x cannot be 1 and x cannot be -1?
yeah, it can't
Okay,
be
because
either.
you put x equals -1.
Well, it's in the denominator, so it's not.
Okay.
So now you have, but the point is, some people just have the wrong strategy in their head. They think when you're asked about continuous, they should be simplifying. That's not a step. Right? So you should not be simplifying.
That means like x equals to 1 and x equals to -1 would be on the multiple choice question, like answer for the final.
Yeah, so they might say, oh, all x not equal to 1. Or they might give you this as the answer. And if you were the person who thought that you should simplify, you
I would
probably
put
pick that
that,
answer. But that's not the answer. Okay, and that comes from, again, knowing what strategy goes with what kind of problem. Simplifying is a technique you would use when working on a limit. It's not a technique you would use when working on this.
So when it asks if it's
Right.
continuous, you always find the domain. Or it's just specific.
For nice functions like this. So if it's a polynomial, you know the domain is all real numbers, it's continuous everywhere. If it's a rational function, so for rational functions, I mentioned this one time. I mentioned for several of them. So go back in your notes and find this. So when you're finding where rational is continuous, it's set denominator equals 0, solve for x.
Mhm.
Any x that makes it 0, avoid them. Then you avoid these x's. Okay. Factoring does not come in play here, right? Factoring and simplifying. You might factor in order to figure out this equation. So in this case, I see that, my next thought is this, x squared minus 1, set that equal to 0, solve for x. You'd have x equals plus or minus 1. Or you might factor first to figure out that it's plus or minus 1. But as far as simplifying the original goes, it's not a thing. I don't care. I don't care what the top is and whether it cancels something or not. That's actually the wrong line of thinking. Simplifying does not come into play when talking about domains or continuity. Simplifying is one of the techniques we apply to limits. It doesn't apply to continuity. So some people saw this and they immediately went into, oh, let me simplify and reduce this mode. Irrelevant. You don't need to simplify. You don't need to reduce. It is a rational function. find where the denominator is 0, solve that equation. Seeing a continuity thing is a solving an equation problem. It's not a simplifying problem. Right? Rational functions are not continuous where the denominator is 0. So that's what you do. This is the thought that you should have had here. Oh, I need to find where this is continuous. What kind of function is it? Rational function? Okay, set the denominator equals 0, solve for x. Where is this continuous? What kind of function is it? Polynomial? Oh, it's continuous everywhere. Oh, you want me to know where this is continuous? Oh, it's a radical function? Oh, it's where whatever's under the radical is greater than or equal to 0. Right? That's simplifying isn't, it shouldn't enter your brain. It's not relevant. Because even if you simplify and cancel, it does not fix the domain. Okay, so people are simplifying and they wrote like one of the answers, it means that they're thinking about it like all wrong. It's not applicable here. If you look at, yeah, here was the problem that we went over a little bit earlier. On one interval is f prime positive, and this is positive at the same time, right? So we kind of looked at that already. So the trick was when you saw that, you should think,
What's increasing?
yeah, so you see this, you think, oh, increasing. Going up from left to right. When you see this, you think above the x-axis. And I want both of those things to happen at the same time. So then you go to the picture and you say, okay, where am I above the x-axis and at the same time moving up as I am going from left to right? Well, it happens here between -3 and -1. It happens here between 1 and 2,
So
and that's it.
So
So the
when-
answer would be -3 to -1 union 1 to 2.
so when it asks for like what interval is like for example this question, we don't care about whether it's an open circle
it doesn't
or
care.
okay. 'Cause
Yeah,
that's
so
what
that
I
was
thought
it.
when I was doing it. That's why I put the
Did you put exactly this what close parentheses?
no, because I thought of it as if it's like
I mean, if you had put this, but you put close parentheses instead, I would have given you one.
no. I mean like you know how like those like that point it was like open circle. It's not like it's
Yeah, for problems like this, I would, the thing is, to be strict, the thing is if you put it on the line, whether this is shaded in or not, you technically wouldn't put it as a point, because when it's on the line, it's when it's equal to 0. Right? f of x is equal to 0 on the line. So whether this point is filled in or not, I wouldn't really include it either way. Right? And so, I don't know, but that's what you should be thinking. You should be thinking, this means increasing, that means above the x-axis. Where does both of these happen at the same time? It happens here, and it happens here, and that's your answer.
Wait, so you said if it was equal to, it would be the brackets.
Pretty much whenever you talk about increasing or decreasing, it's never going to be included.
Oh, okay.
It's kind of one of the things you would know. Because whether or not it's closed circle or open circle, it would be irrelevant to the question. You still would want to be above that circle.
Is it important to know that, or should you just like disregard that and just like put it as an interval?
It would be important to know that if they ask something like this, greater than or equal to. Now it's like, I need to put that.
Right.
but if it's no equal to, just put it as parentheses.
Yeah, it means whether that point is shaded in or not, you still wouldn't include the point because you want it bigger than that.
But
But it
most
would
of the
never
time
be-
they only put like
But usually
greater.
they put like this. So I would just think of open parentheses all the time. It's more of a conventional thing. We normally think of intervals of increasing as open parentheses. So that would be that. If you wrote on anything similar to that, I would have given you. But some people are putting numbers like 4 or 5. Like, what are you talking about? Like it's an interval. Okay. But yeah, so when I see that, that's what I would think about. What about here? The second part, 6. At what x values is the function continuous?
Oh, it's not continuous.
Is not continuous, correct. So where would this be
-1,
not
1,
continuous?
and 3.
So let me get rid of this first. So you need to learn how to read the pictures for this one. So remember, continuous, it's not continuous when there's any break happening, right? So obviously here there's a hole and there's an asymptote.
That's what
Here
we
there's a
started.
hole. Here there's a jump.
Which is no.
So those are the places where it's not continuous. So it's not continuous.
At x equals -1, 1, and 3.
At x equals -1, at x equals
1,
1,
and x equals 3.
3. Right? Now your reasons, you could say, oh, this is a hole. You could say, yeah, this is a hole, this is a hole, this is a jump. But there are holes at all the locations. I actually didn't really look at the reasoning. I just say, if you could tell me the points, I'm happy. I'm not even going to read. You could have said, oh, because of unicorns, and I would have given you the points. I was just, can they know the numbers? I would have been happy if you know that. Now the follow-up question
That's the
is,
smaller one.
at what x values is the function not differentiable? Okay, so remember what that not differentiable. Okay, so now once you want to talk about not differentiable, and here's where, I'm not sure if anyone got this right actually.
I put x equals, well, I got the other version.
So once you say not differentiable, you need to remember a very important fact. A function is not differentiable when it's not continuous. So literally all the answers here should be carbon copied over there, which a lot of people just ignored completely.
Oh, that's
That's
why
what
you.
I did.
So
you
it
got
should be
that right.
this,
Yeah, but you have to read 2 points.
this,
I put the same
this.
things.
but then there was an additional point,
Oh.
right?
was
Most
an
people
additional point,
saw
that's
the
why.
additional point and they
Oh,
didn't
okay.
copy the original answer. If it's not continuous, it's not differentiable. Every answer here automatically falls over there. However, the derivative is a little bit more picky. There are times when it will be continuous but still not differentiable. And so for the differentiable, there's an extra point. The sharp corner is also dangerous for a derivative. So you'll add to this list x equals 2. Now a lot of people just put x equals 2 as the answer. I'm like, what about where there's a hole? You think you can draw a tangent line where there's a hole? No. So once you figure out not continuous, that automatically means not differentiable.
So refresh my. So if it's not continuous, that means it's not differentiable for
Yeah,
sure.
but the other way is not true.
Okay.
Because you see here, I'm not differentiable at x equals 2, but I am continuous there, right? So if you're not continuous, you're definitely not differentiable, but it doesn't work vice versa. Okay? So your differentiable list could have extra stuff in it, right? The differentiable list is going to be longer, because the differentiable list is not going to work everywhere this doesn't work,
So
but it's also, there are additional places where it's not going to work. And so
So what's the answer?
a lot of people figured out that this is the answer, all 4.
Okay.
So this is, all 4 of these is the answer. So there were 3 things in the not continuous list, there are 4 things in the not differentiable list.
Wait, x equals to 2.
And what's like a valid reason that you would give back someone credit for?
Give reasons.
For this one,
Yeah.
so the reason for the first 3 is not continuous.
Yeah.
So I would just put like this, not continuous, that's the reason. And then I would say here, sharp corner.
So if I put what is the reason?
Well, these are not the same reason. Like this is continuous.
So you actually read that.
And not this time around, no.
Oh, okay.
But the thing is, I don't think anyone had all 4 in the list.
Yeah.
I don't think anyone answered it. I know a lot of people answered the 2, they pointed out the sharp corner, but they forgot to copy the answers from here.
Like cusp.
Yeah, cusp is another word for sharp corner. So that would be the same. Anything else? not differentiable. Oh, limits.
Oh, I messed up on that.
This one wasn't that bad. I actually think a good chunk of the class actually got the limits correct. There were people who got it wrong, but I actually don't think was the majority of the class. Problem 8, most people actually got it right, I think. More than half people got it right, for sure. So one from the right, limit as x approaches -1 from the left, limit as x approaches 1,
For these.
I didn't do much on that.
and the limit as x approaches
Oh, I
3.
did, I did.
Okay. Let me scroll back to the picture so we can look at that.
Yeah, I keep forgetting to write f of x.
Yeah.
Okay, so I want to find all these limits. Okay, so -1 from the right, where are you looking?
To the
See, you identify
The right.
-1,
-1.
you ignore the left side, you only look at the right side. What is happening to the graph as you come from the right?
It does not. It's like going up.
It's going up,
To infinity.
that's infinity. -1 from the left. So identify -1, only care about the left. What is the y value getting close to when I come from the left?
Negative.
2.
Oh. I mean,
The y value is
it's
getting
2.
close to 2. What is the limit as I approach 1? Well, if I come either from the right or from the left,
SB1.
it's approaching a point over here, which is not exactly clear what the graph is, so I did grade this kind of leniently. If you told me any number strictly between 1 and 0.5, I would have given you the answer. So a lot of people thought of it, 0.7, some people put 3/4. I gave both of those answers correct, because it wasn't to scale, you wouldn't have known what it is. So if you said something like 0.75 or 0.7 or 0.6 even, I would have given you the point. What about 3?
It's the same.
3/4.
Huh?
3/4.
It does not exist. Why does it not exist?
Because if you're
If you're coming from the
both
left,
sides, yeah, it's
your y values are down here.
Yeah.
But if you're coming from the right, your y value is up here. They don't agree.
yeah, that one I wrote.
All right, so that comes from you need to know about the concept of limit. For the limit to exist, both sides have to match up. So the limit here existed. The point that that's an open circle is irrelevant. Limits don't care. You just care about getting close. Come from either the right or the left side, the y values are converging to the same number. Here they're not. The right side goes to this, the left side goes to something below it. So it does not exist. Similarly, if I had asked you what is the limit as x approaches -1, the answer would be does not exist. Because from the right, you're going to infinity, from the left, you're going to 2. Those don't match up. So yeah, so we got like 4 problems out of this graph. Normally they might ask you two of these like on a final, but I wanted to know if you know how to do all of those. Okay, let's talk about this one, because this is another one where a lot of people just went all over town. So there are I've seen some crazy responses for this problem right here. Okay, so you're reading this. What would you see?
Wait, what question would that be for this other version?
I don't know for the other version, but focus on version 8. What I'm writing on the board, you should be writing it on the blank, right? I don't want you to copy the solution. I want you to actually write down the thought process in the blanks. That's why I gave you a blank copy of the test. Okay, so you're reading this. What do you think? What's the first thing that comes to mind? What do you notice?
Tangent line.
Tangent line. Okay, good.
Equal to each other because it's parallel.
Parallel. Okay, so parallel means same slope. Tangent line means need the derivative. And I need the derivative to have the same slope as this. Now what's the slope of this? 9. In other words, putting all these ideas together, I want f prime of x equals 9. Now I look at the function. Okay, what if f of x is blah? Where's the tangent line parallel to this line? Okay. Tangent line is what I noticed. Oh, to find the tangent line, I need to find the derivative because that's how I'm going to find the slope. And I need that to be the same slope as this line. The slope of that is just the m, y equals mx plus b. So that's 9. So this is just a fancy way of saying, where is the derivative equal to 9? So you're just going to find the, now you go and you look at this, what's the derivative? 3x squared plus 6x, set that equal to 9. You're going to solve that. That's what we're done. So in the solutions, I started, I don't know what I wrote down, but I probably started here and wrote the answer. And so I want you to understand what went through my head when I started writing down that answer. I literally read this, find the x values where blah, the tangent line is parallel to the, oh, tangent line. Okay, I need to find a derivative, parallel, that means same slope with what? Well, with this line. Okay, what's the slope of that? 9. Okay, so I need this tangent line to have the same slope as that, which means the derivative gives me the slope of the tangent line. So I set the slope of the tangent line equal to that. And then I start worrying about the specific function afterwards.
So was it x equals -3 and x equals 1?
I don't remember.
Oh.
The point is, this is the equation, you should have set it up and solved that. But a lot of people are doing a lot of other. I have people setting this to 0 or doing some other things.
Oh wait, so you don't put -9 on both sides?
What?
You don't subtract the 9?
Sure, yes, if you wanted to solve this, yes.
Okay.
Again, maintain focus here. I don't care about the solution to the actual problem, I care about the thought process. I don't want you guys to be there trying to write down solutions. Right? Pay attention to where the solution came from. I'm going to assume that everyone would know how to solve this from this point. I want you to know, the thing is, not everyone knew that this was the equation they should have set up. So you need to pay attention. How would I know this is the equation? Right? You need to be taking notes on that for yourself. Write it in your own words. Here's how I would know that that would be what I need to do. Right? So I'm explaining to you, and what you should be writing in the blank space is literally in English. I don't want you to be writing out the math. Write out your thoughts. Okay, I would think about this, then I would think about that, then I would think about that. I want you to actually fill in the blanks with thoughts, not with the solutions. I already gave you the solutions. You can see the math written out if you want by going to Blackboard. That's not the point of this exercise. Okay, let's look at, say, 10. This is also another one. And what would you guess was the problem here? It's just derivative.
Yeah.
A lot of people just didn't know what this phrase meant. Even though I sent an email saying, oh, make sure you know what this term means. It's exactly the same as derivative. It's a synonym. The derivative is the instantaneous rate of change. So when we did derivatives, after we did the definition, I wrote down some phrases that you can think are synonymous with derivative. So I'm saying derivative means slope of the function, or slope of the tangent line, or the rate of change of the function, or the instantaneous rate of change of the function. They're all these phrases that they're just another way of saying derivative. Right? Instantaneous rate of change happens to be one of them. So had you seen that, it would be really easy to understand what the solution is. It's just g prime evaluated at 4. So here, this is just g is equal to 2x to the minus 3 over 2. Use the power rule, plug in 4, that's the answer. So you find g prime, and then you plug in 4. And that's basically it. But a lot of people got that question wrong. A lot of people were all sorts of things. So at this point, you should be writing down in the blank space, instantaneous rate of change is another phrase for derivative. Okay, here, I actually had a few people getting this right. So this was one of those where a little bit more than half the people got it right. So I told you a piecewise function, f of x is this function, find the limit as x approaches 2 from the right. So the first thing I'm going to realize is limit as x approaches minus 2 from the right. So yeah, I notice I'm approaching minus 2, but it's very important that I realize I'm approaching from the right. Okay, of f of x. So now, when you see from the right, what do you think here, from the right?
I would find which part of this, which like function would match with that negative, like
Yeah, but what does it mean to be negative 2 from the right?
that has to be on the right side.
On the right side of negative 2, so how would you actually think about that? Once I see
It
this,
has to be
It has to
greater
be
than negative 2.
right, you would think a little bit bigger than negative 2.
So the full.
Right? If I said from the left, I would think, oh, I want to be a little bit smaller than negative 2. Right? Now once you have that, you understand, oh, I really care about my x values being larger than negative 2. And so you would look at what would, this is what applies here, so it's the middle one. So the limit of that as x is approaching minus 2 is just the limit of this expression.
You just plug in negative 2.
And you just plug in. So you have, so you see this, you think that, it identifies the function you want to find the limit of, and now you ask yourself, how would I find that limit? Step 1, plug in. That's the first thing you think about when finding any limit. So, and it works here. I can just plug in negative 2. So this is just going to be 2 plus negative 2 minus negative 2 squared, and whatever that answer is. Okay. So that's, when you read this symbol, you want to think of it like that. Okay, limit as x approaches negative 2, you want to, if it was just negative 2 with no plus sign, how would you think of that?
I would,
And it would just apply to all of them, right?
We would apply to both sides. You have to check each side, right? So you look at when it's a little bit smaller than negative 2 and when it's a little bit bigger. And the hope would be that these guys match up, right? Now does this actually match up? Because this would be minus 4 here, right? What if I ask you the limit as x approaches negative 2 from the left, the function? That means I would just plug in negative 2 over here, so that would be 2 plus 3 to the minus 2, and that's not the same, right? So overall, if you just ask me about negative 2, I would say it does not exist. Negative 2 of f of x does not exist, because the left and right don't agree. However, when you see the little plus sign or the little minus sign, you should think to yourself, plus sign means I want to be a little bit bigger than. Minus sign means I want to be a little bit smaller than, right? I want to be on the right versus the left, and another way to say that is a little bit bigger than it or a little bit smaller than it. So that's an important thought that you should be having when you're looking at this.
So if we got negative 4, the answer would be it doesn't exist.
Come again?
So we got negative 4 when we plugged in. Is that
This is the one-sided limit. This is from the right. This is from the right, it's negative 4. From the left, it's negative, it's this, right? Which is 2 plus 1 over 9. So they're not the same. That wouldn't be 4. So the question is, if you're asked this with no sign, no plus or minus, that means you have to worry about both the right and the left, and they have to match up. In this case, they did match up, so if I ask you this question, the answer would be does not exist. If I ask you this question, that's the answer. If I ask you that question, it would be minus 4. But on the test, this is what you're asked, so minus 4 is the answer. Yeah, these two really confused a lot of people. Okay, let's look at this one. Yeah, so these two problems, 12 and 13 on version A, requires you to know a lot about continuity, the technical parts about continuity. In fact, for this it requires that you know that continuity means continuous at because this one they're asking you to redefine a function. So that makes it a little bit more complicated. Here you need to remember continuous at x equals a means the limit as x approaches a of your function is equal to the value of the function at the point. So in other words, when they say, what do you need the function to be at -3 so that it's continuous there? That immediately means you want the limit as x approaches -3 of the function to be equal to the function at -3. And this is what you need to find. And then after that, it's actually not so bad. All you want to do now is find this limit. So you're that. Now you want to find that limit. How would you actually do it? Right, you try to plug in, that's the first thing you think about, but then, yeah, division by 0 happens. So what do you do now? So you try to factor and simplify. So this is just the limit as x approaches -3. How do you factor 9 minus x squared?
Don't you do like
Negative.
and then x squared minus 3?
So it's x plus 3.
So it's just 3 minus x
X.
times 3 plus x.
Yeah. I like to do it the other way.
Okay, doesn't matter. This would cancel. And now you plug in -3 for x, right? And what would you get here? So there's a 1 on top. If I plug in a -3 here, it's negative a -3, I get a positive 3, 1, 6 is your answer. So that one was somewhat technical. The thought you really needed to know was the definition. That's something you should kind of know anyway. Alright, so if it's a little bit technical, they might ask you, where is this rational function continuous? It's just a matter of saying denominator equals 0, solve for x. The thing is, they know that it's discontinuous. They want you to force it to be continuous at a certain point. It means you need to force this equation to work. So that means your f at the point -3, you need it to be equal to 1 over 6. Then that would mean it's equal to the limit, and that gives you the answer. Okay, so 13. I saw a problem like this on a couple of sample finals, but we actually went over it. But we actually went over examples like this in class when we first started limits, like the first day. I went over an example like this. Let's see, maybe 3 or 4 people got this right.
I chose, well, for the other version, I chose,
What do you think the answer is? Where's this continuous?
C.
Yeah, it's C and then remove this.
Yeah, non-removable.
Isn't it A?
Wait,
It is A. It's continuous everywhere.
So it's the other,
All because
so it's
one's a rational
Because what's the problem here? When x equals 1, right? You divide by 0, which is bad.
But you can remove it.
But you can remove it. Now, that means, so if you look at this as something that you can remove, this is x squared minus 1 over x minus 1. This would be x minus 1 times x plus 1 over x minus 1. You notice that you can cancel this, right? But it doesn't fix the problem technically. It creates what you call a hole. from earlier. So it means your function looks like x plus 1 except at that one point.
But since it's removable of discontinuity, right? That means it's continuous everywhere technically.
No, that's not why.
Oh my god.
What makes it continuous? Do you see now what makes it continuous?
Like when I solved it, like if I plug in x equals 2, it equals, well, mine is a different version. When I plug
Right,
in,
but if you take the limit of this as
it
you
equals to
approach
2.
1, it actually equals 2. And they said, hey, if x equals 1, let's force it to be 2.
That's what
You see that?
I had that, but I changed
So
my answer.
basically it means someone went to this graph and they filled in that hole.
Oh, so whenever
So
we
hey,
have this.
now it's continuous.
Okay.
If they had put any number here other than 2, like I could have put the number 4, and the answer would be, yeah, it's not continuous. It's continuous because they filled in the specific point they needed to fill in. Right? So this function by itself has a hole when x equals 1. However, they went to x equals 1 and they filled in the hole. So it's actually now continuous everywhere. I can now draw it without lifting my pencil off the page. I believe,
Wow.
I think in the other version I made it continuous as well. Although
Yeah.
I put a different function and this
the
number was
same-
4.
Yeah.
But the same concept would
It's
show.
x squared minus 4 over x
Yes.
minus 2.
So if you showed your work right there as your justification, is that valid? Or would you need to actually write something else?
Yeah, you could write something like, oh, we filled in the hole. Or you could draw a picture like that with a circle and shaded it in. Or you can write down the fact, or you can state, technically the reason would be this. The limit as x approaches 1 of our function is actually equal to f of 1.
So we get, for the justify, I can just write that and not
Yeah, you
use
can write
words?
whatever. Yeah.
You don't need to use words for those? Okay. Right. I didn't know that.
Yeah, justify is just explain. Just explain what you're doing.
I can
I'm
explain
not looking
using, I can explain using equations, right?
Yeah, to explain using equations, you would have done this.
Yeah.
You would have shown that this limit is equal to the value that they told me it was.
Yeah, it's just like showing work then.
Yeah,
Okay.
but it's okay. I had some people actually write down, oh, with this I
It
can
gets-
draw it without lifting my pencil off the page. They literally wrote that down. I'm like, okay, cool. And yeah, I gave, someone actually wrote that down and I gave them the point. Okay, horizontal tangent line, we dealt with this situation again already. It just means horizontal tangent line means slope is 0. So this means the derivative is 0. Solve for x. Right? Now I go and worry about what this says. Like that's the phrase that stood out to me. That's the first thing I would start to focus on. What does it mean to be a horizontal tangent line? That's what I would ask myself. It means the slope is 0. But what does it mean the slope is 0? Well, the derivative is the slope. It means the derivative is 0. And so then I would immediately go to 5x to the 4th minus 5 equals 0. And then I need to solve that equation to find the x's. Okay, now here's where I ask you to literally use the limit definition. And at this point is where you
Okay, that was.
just plug in
Yeah,
the
that's-
limit. Don't use this unless you're specifically asked for it. It's a huge waste of time. Okay. Now, it turns out in a final they'll actually never ask you to find the derivative this way, but they sometimes ask you to find the difference quotient, which is, most of it is the same
So
work
the
except
difference quotient is the same thing as saying the limit that
the difference quotient is without the limit.
without.
So if you just write down, sometimes when I give you this function, they'll ask you, find f of x plus h minus f of x over h, or find the difference quotient. And that's just you doing this. If they say find the derivative, it's just one additional thing, right? After you simplify, plug in h equals 0. That's the only difference between them.
But you did it right.
So I do want to make sure you know how to compute and simplify this, because sometimes they'll ask you for that specifically.
You just forgot to plug it.
But normally if you're finding a derivative, you don't want to do this way. It's not efficient. It's important, it's the definition, but we know shortcuts now, so just use the shortcuts. Right? You only do the long way when it's specifically required. In here it was specifically required.
So
And it
that's,
says no credit for any other.
so,
So if you just did the power rule here, which is you could find a derivative, you would get 0 credit.
so that is
Wow.
the limit, the definition of a, like,
This is the limit
Different-
definition
yeah.
of the derivative.
can you show the difference quotient you're talking about?
The difference quotient is just this part without the limit.
Without the h of
This
the
part here is called the difference quotient.
Oh.
This is the difference quotient of them. Now, once you take the limit of the difference quotient as the denominator approaches 0, that's called the derivative. Right, so without the limit, it's just called the difference quotient. With the limit, it's now a derivative. Right, so it's like Clark Kent and Superman. With his glasses, he's Clark Kent. Without, he's now something much more cooler. So you throw a limit in there, the difference quotient now morphs into the
So
derivative.
the different quotient is cooler.
It's a cooler.
Huh?
The different
Yeah, it's like a
quotient is
reverse
cooler.
Superman. Like if you remove the limit, he's just the difference quotient. He
I
actually
hate
gets
radicals.
stupid. Maybe a Green Lantern comparison would have been when he takes off the ring, he's stupid. When he puts on the ring, he's something like that.
So when you,
So if someone asks you to compute the difference quotient, it's just the f of x plus h minus f of x over
Without
h.
the limit.
Don't plug in h equals 0 at the end, don't do anything.
Or else
Just
it'll be wrong.
simplify that. If someone asks you to find the derivative, you have to take the limit as h approaches 0, which means after you simplify, plug in h equals 0.
so when it says find the limit, you use the limit definition and it just tells you to find the difference quotient, you just use that and
The
plug
formula without the limit.
in without the limit.
Yeah,
And that will be the answer after you simplify?
yeah,
Okay.
Javon,
yeah.
is the final heavily concentrated on this stuff as opposed to like the earlier material?
There's some
we learned
matrices,
and
there's some
and
like,
course?
Uh,
Like supply
they make
demand
new ones every
function.
year, right?
I would say three-quarter of it would be the calculus part, maybe a quarter of it is the matrices part.
Do you think this is the hardest part or matrices?
Oh, this is for sure harder than.
Oh no, I'm saying like the stuff we learned in the beginning, like profit, revenue, cost, functions. all that.
Oh, no, those definitely show up. Like
I know
marginal
you do all
cost,
that.
profit, revenue.
Yeah, no.
Yeah, those will show up. Depreciation, yeah, those are.
Oh no, I already
yeah,
forgot
definitely.
everything.
I have everything. I forgot. to
Don't
do
worry,
it.
at the end, we're going to review everything. We're gonna do some mock finals and we're gonna talk about it. And yeah, I am gonna get you guys used to the final setting, so I'm gonna come in with scantrons and the whole works, and you guys are gonna sit here and fill in scantrons. And I want you guys to get used to what it's gonna feel like to do the final. So don't worry, we'll go back. But for now, just learn what we're doing now and don't worry about it. We'll eventually go back.
You'll see the difference between your exam and the final.
Yeah, let's see. Well, hopefully what I'm doing now is gonna make you guys better, so I hope to see a difference between now and the final. Yeah, and it's the calculator section. I would literally just plug this into my calculator. So there's nothing really to talk
Wait,
about here.
so
And what I did here, I actually did it both ways, even though I don't recommend doing it by hand. But I typed out, I wrote out the commands that I would do, so I
wait,
would
I
just,
have a question.
yeah.
How do you type like x is approaching to 3 to the right? Like
You put a 1 at the end. So if you want to say, if you want to write the limit as say x approaches 3 from the right of the function, in your calculator you access the limit command. You would type out the function. You would put comma, x is approaching 3,
3,
and then you put a 1. And that tells you from the right.
and then another comma 1 from the right.
If you want to go from the left, you would
You
put
put
a minus
negative?
1.
Negative 1?
If you just want the general limit, you wouldn't put anything at all. You would close the parentheses here.
So if you just without left or right, just put the 3, like for example.
Yeah, so if it was the limit as x approaches 3 of the function, it's just going to be the limit command, type out the f of x, comma x, comma 3, close parentheses.
That's what it kind of.
Now, if you're going from the right,
That's
you would
all.
add a comma 1. If you're going from the left, you would add a comma minus 1.
I actually got lucky. Like, I just I forgot to put the what's it called, the 3 or 1 or whatever. I just put x, and since the limit came up, I was like, okay, so it's 0 on both sides. So I just put 0.
Yeah, but that's because in this particular example, the limit as you approach 3 from the right was actually equal to the limit as you approach 3. If it was one of those situations where it did not exist, you would have gotten it wrong. Yeah.
But he was lucky.
Yeah, it turns out the two sides actually matched up in this problem.
Another.
So you got lucky here. But yeah, so
Sometimes
for
I'm
this
guessing.
one, I would do the calculator. For this one, I would plug into my calculator. This one, I plug into my calculator. Yeah, I'll use it's straight up calculator, which you guys can look at. But hopefully what I wanted you guys to do this time around is to not only write out the solutions, write out the thought process. You want to really know how to translate a phrase into a mathematical
Do you
idea.
think it's gonna be morning final or like afternoon?
I wrote out the schedule. I know the final schedule
It
is
says
up.
to be like, to be on.
No, it
It's
definitely, we know
confirmed?
the schedule for sure.
Oh, okay.
If you can Google Baruch final exam schedule, it's definitely there. I can look it up and tell you later. Anyway, that's it for now.